All right. People are still trickling in, so I will slowly get started and working things through. What we're going to do here is a couple of things where we're going to build up polynomials from this. I want to run this in reverse because it gives us an idea of things you'll actually see with data when this comes about. And so what we're going to do is we're going to look at how we can build polynomials from having a little bit of data. And specifically, what I want to do here is I'm going to start with some graphs. And what we can do when the graph has a value. It's funny, this is actually something that I've used more than I thought I would, because you'll get people that will plot graphs and you're trying to figure out what equations they're using or where did it come from, because you need to know the kind of the rule underneath it. And this actually works really easily. Well, easy's a relative term, isn't it? It works fairly straightforwardly. How's that, right? Yeah, the method makes sense from what we've learned about roots. And the key to any of these things is whenever you have data and you want to get a polynomial out of it, you need one more piece of data than the degree of your polynomial. So I'm looking at this first graph here, which has number 3 on it. And we're just going to talk about what we know about polynomials, what this whole chapter has been telling us about polynomials. So it starts at negative infinity and ends at positive infinity, right? We're starting down here at negative infinity. As we move, we're going off towards positive infinity. That's the end behavior of this function. So it has to be an odd polynomial. This has to be an odd polynomial because of that behavior. And specifically, the leading coefficient has to be positive. And if it was negative, it would start up here and run out here. So just what the graph is doing is telling us some things that the polynomial will do. And this really helps us if you're sitting in, you're watching someone talking about this graph here, and you're worried about this dip in the middle, but you know that it's going to shoot off towards infinity if it keeps moving, if the rule that defines this polynomial is good for the domain of all real numbers. Well, so let's look at what we have here. We have 1, 2, 3, 4, 5 roots. It crosses the x-axis 5 times. And none of them bounce off of it with a multiplicity. They're all completely crossed through. So I can look, what is this? This is negative 3, negative 1, 0, 1, and 4. That's enough to give me the factors. I can find the factors of my polynomial with these roots. But what I won't be able to find is the a sub n. Oops, get over here. Won't be able to find the a sub n. A sub n unless I know one other point. And normally what you can do looking for one other point is you can find, and on this one, for some reason it cut off, I followed the 5 up and found that it touched an even place. F of 5 equals 6. And this gives me enough information to make the polynomial. And so generally I look at it, if you have some piece of data, you need, if you have 5 points, you're going to get a 4th degree polynomial. If you have 6 points, you're going to get a 6th degree polynomial. If I have someone's graph and I can count up their roots, I can develop a polynomial for it. So all real solutions coming through here, I'm going to use these roots to write it through. So let me come over to here. And let's see. I had x equals negative 3. X equals negative 1. X equals 0. 1 and 4. And I knew that when x was 5, my function returned 6. Those were all the things I knew about this function from its graph. All right, so let's use all this information to help us, and we're going to use the completely factored version of a polynomial. The completely factored version said, hey, if I have some f of x, I'll have some a sub n out front, and then I'll have x minus c sub 1, x minus c sub 2, and so on until I get x minus c sub n. Well, I have 1, 2, 3, 4, 5, so this is going to be some a sub 5, right? 5 coefficients. And I have x minus 3, or x plus 3, x minus 1, x plus 1, x minus 0, I'll get a lowly x in the middle there, x minus 1, and x minus 4. So knowing these roots, I can start writing for the polynomial. My big quest here is to figure out what a sub 5 is. What is the leading coefficient? Right, I have an infinite amount of polynomials this could be, but the leading coefficient is going to shape how quickly it rises and how quickly it falls. So I'm going to go, well, I could multiply all these things together, and then multiply everything by a sub 5, and then I could plug in my x. That's going to be really messy. So what I'm going to do is I'm going to look at what is a sub 5, or what is f of 5. Well, f of 5, I would put 5 plus 3. 5 plus 1 times 5 times 5 minus 1 times 5 minus 4. But we know that f of 5 is equal to 6. And now all of these have turned to numbers. I don't have to worry about anything being cubic or quartic or quintic or whatever nth power I have there. I have a series of numbers and my variable. So I'll put my 6 on my left hand side for right now. And I'm going to just multiply all these numbers. So 5 plus 3 is 8. 5 plus 1 is 6. 5. 5 minus 1 is 4. 5 minus 4 is 1. And they're all times a sub 5. So 8 times 6 is 48, and 5 times 4 is 20, times 1, and 2 times 48 is 96, or this is 960. Alright, calculator, verify, right? One of those moments where I just ran through everything without a calculator. I hate when I do that. But I want to solve for this leading coefficient, so I'm going to divide both sides by 960. And I get 6 over 960. And that is equivalent to 1 over 160. So I have found my leading coefficient. And I can plug that back into here, and I have my polynomial. Alright, well, let's do the hard part of this then, because we can. And I'll only do this one to show the hard part. This is not the way we normally write our polynomials. We wanted a coefficient for each term, so let's FOIL. So x times x is x squared. X times 1 is 1x. and a positive 4x. That gives me 5x in the middle there. All right, doing my FOIL, and 4 times 1 is 4. So these two terms have combined, and I have an x minus 1, and an x minus 4. I think I'm going to do the x minus 1 next. I'm going to leave this x towards the end, because it's going to be our easier multiplication, because it's just a monomial. So I'm going to do x minus 1 times this. So I'm going to multiply the x times each term, x cubed plus 5x squared plus 4x. I'm going to take the negative 1 and I'm going to multiply it by each term. Negative x squared minus 5x minus 4. And I still have the x minus 4 and the x hanging outside. Well, I'm going to collect like terms. So I only have one x cubed. I have a positive 5x squared and a negative x squared, so that's positive 4x squared. I have a positive 4x and a negative 5x, so that's negative x minus 4. Oops, my 160 looks like eyes. 160. I might be needing to get a new tip for my stylus pen, I've noticed here. And we'll see if I can just trim this down and make it work. Alright, so I'm going to take my x and I'm going to multiply it by each term in here from the x minus 4. So I'm going to get x to the 5th plus 4x cubed minus x squared minus 4x, right? This is going to each term. Then I'm going to take the negative 4 and I'm going to multiply that by each term. So I get negative 4x cubed minus 16x squared plus 4x plus 16. All right, negative 4 times that's 16. That's positive 4, negative 16. Yep, we're good. And then x on the outside. Going to collect like terms. So I only have one x to, whoops, this should have been x to the 4th. Right, x times x cubed is x to the 4th. My bad. So x to the 4th, I have a 4x cubed and a negative 4x cubed. So that goes away. Those two terms cancel each other out. Yep. And then I have a negative x squared and a minus 16x, so I get a negative 17x squared. Right there and there. And I have a negative 4x and a positive 4x. They cancel each other out. And plus 16. I'm going to multiply the x through. I get x to the 5th minus 17x cubed plus 16x. And then they'll each get this coefficient. Coming across. Might have made a sign error in there. And we can redo the foiling. I would be happy here. Always happy here, because that's something I can compute. Alright, so there we have built up from the rules that we had. Let's look at two more applications of that idea. Oops. That's interesting. My browser window switched on me here. Let me fix that. That's better. I'll come back here. And we're going to look at this last one, number 13. So, if we know that we have a fourth degree polynomial with real coefficients and the roots of 2i and 2 minus I. So x is going to equal 2i, and x is going to equal 2 minus I. So let's bring that over to our blackboard here. And I have, these are two known roots of a fourth degree polynomial. So again, I'm kind of thinking, don't even really have to think of the fourth degree polynomial. What I kind of have to worry about here is I've got two different complex solutions that will give me their complex conjugates. So that means I get this and I get this, because those are the conjugates. Now notice I have 4 answers now, so I don't have any other roots I need to hunt or find. I've just got to combine these together. And I'm going to look at them in parts. I'm going to look at this conjugate pair as one part, and I'm going to look at this conjugate pair as another part. I'm going to turn those into quadratics, and then I'm going to multiply those quadratics together. So I'm going to turn this into its factors. So I get x, whoops, wrong color. I want this to be orange because I'm going to keep my parts separate here. This is x minus 2i for the first factor, and x plus 2i for the second factor. So I'm going to have x times x, which is x squared, right, firsts. My outers and inners will cancel. That's the whole purpose of the complex conjugate. And I'm going to get negative 4i squared, or x squared plus 4. And so that's going to be one of my quadratic factors that I have. This one here, in green, if I turn these into the factors, I'm going to get x minus, well, I'm going to keep this whole thing in parentheses. That's the first factor. I'm going to subtract 2 minus I from both sides. So it gives me x minus 2i. I'm treating this whole thing as one number, and I'm pulling it over as one number. So that's my first factor. And my second factor is x minus 2 plus I. Alright, so here there's going to be some nastiness going on. Right? So I kind of want to, I'm going to use different symbols to deal with everything in the parenthesis being one number. Right? You don't have to do it this way. We can multiply it out using FOIL and making sure that we carry the parentheses across for each term, and that will work for us. But I'm going to use some shorthand here. Right, and so back in chapter 3 we said a complex number z equals 2 minus I. Its complex conjugate we would put a bar over top of, and 2 plus I. So I'm going to rewrite this as x minus z times x minus the complex conjugate of z. I'm doing this so that I can focus on these things kind of individually. So if I do my first part here, I get x squared. Right, firsts. My outers, I'm going to get minus the complex conjugate times x. My inners, I'm going to get minus my complex number times x. And then in my outers, I'm going to get plus z times its complex conjugate. I am not trying to invent any new way of doing mathematics here. This is FOIL. What I'm doing is I'm using this variable z to just save me having to deal with what's in the parentheses until I have to. Now, something we knew about the complex conjugates is when I multiply a number by its complex conjugate, I get the first part squared plus this part squared, or 1 squared. And so the answer is 5. Right? This always came out of our complex conjugates, and I'm going to show over here in blue what that came from. If I have a plus bi times its conjugate, complex conjugate, I get the a squared, the middle terms cancel, and I get minus bi, both of them squared, b squared, I squared. But I squared is -1, so it becomes a squared plus b squared. We always get that when we multiply something by its complex conjugate. So this is going to give me 2 squared, because that's the a, and this is the number 1 for b, so I'm going to get 2 squared plus 1 squared, or 5. So a reason we spent some time staring at complex numbers in Chapter 3. That's 5. I know it's going to be 5. It's going to be a positive 5. Alright, so now I have to just worry about the parentheses here. I've taken all that ugly stuff I had in the parentheses, the 2 minus I and the 2 plus I, and at least for the front and the back part of my quadratic, they're taken care of. Now I have to worry about the middle terms. And the thing you will find is the middle terms is where all the mess always ends up. The first and lasts are usually the easier bit. So I'm going to put my minus sign here, and then I'm going to put my 2 minus I. Or 2 plus I, I'm sorry, because it's Z bar, 2 plus I, times X. Now I put my minus sign and my 2 minus I, times X plus 5. I'm going to distribute the X inside. I'm going to distribute the X inside. And now I'm going to distribute the negative across. And look. My imaginary parts cancel each other out. It should have. Right? The fundamental rule of algebra says if I have this conjugate pair and I have real coefficients, I'm not going to have any imaginary terms come out. They have to cancel each other out. And by multiplying by complex conjugates, I guarantee all of the imaginary parts come about. And so I have x squared minus 2x, that's minus 4x, and plus 5, because the imaginaries cancel out. And so there are my two polynomials. So I'll multiply x squared through each term here. So I get x to the 4th minus 4x cubed plus 5x squared. I'll multiply a positive 4 through, so I get plus 4x squared plus 4x squared. What am I looking here? Looking for a sign error on this. Sorry. Just making sure my signs are right. X to the 4th minus 4x squared plus minus 4x cubed plus 5x squared. There's what I was missing. Alright, so x to the 4th minus 4x cubed plus 5x squared. 4x squared minus 16x plus 20. let's see here. I'm double checking everything. X to the fourth minus 4x cubed plus 5x squared. So x to the fourth minus 4x cubed plus 9x squared minus 16x plus 20. Here, I'm double checking my signs. Always double check for a sign error. X squared minus complex conjugate x minus complex number x plus zz. That's good. X squared, so minus 2 plus I, so negative 2x minus ix. That's good. Minus 2x. Yes. Those cancel out. That gives me that and that. Yep. And so we've got our solutions. I get 1, 2, 3, 4 sign changes. So I have 4, 2, or 0 positive reals. And because I started with imaginary, I know I have 0. I knew I needed an even number of sign changes, and that's what I was double checking. Using my Descartes rule of signs to double check. All right, 1, 2, 3, 4. So 4, 2, or 0. And because we started with all imaginaries, we know 0 had to be the answer. All right, and this is what the first 5 sections do. They tell us how we can tear apart these ugly things and how we can build them back up. Alright, I'm only going to prelude a little bit into this chapter 4.6. I'm only going to do just a little bit of this. I want to define what we're doing with and really launch into it next Thursday. We'll have homework that takes us all the way up through 4.5 by the end of next week. Definitely read 4.6. But I want to kind of get an idea of how all of this is going together. And so we're going to have a thing called a rational function. There we go. What happened over here? Something happened over there. Alright, there. Now it's not doing the weird arrows. And so we're going to have a rational function. And so we're going to define this new thing. So polynomials had their form where you had your leading coefficients, you had your powers of x, and you descended. A rational function is going to be some function of x composed of another function of x divided by a second function of x. And this is really hinting at a thing that we're going to start doing more and more is this is a function and this is a function and I'm dividing them. I can do algebra with functions. And the result of a division or an addition or a multiplication of two functions has meaning. And in this case, we're going to look at a rational function where we have this division. And I think the first thing that whenever we start talking about dividing from our concept, we have to realize that we cannot divide by 0. And I want to say P of x and Q of x are polynomial functions. Where Q of x can equal 0. So we have now made a new function that is not a polynomial. It's made out of two polynomials, and I am dividing one by the other. This bit here means we need to know what values x equals 0 at, because we have to exclude them from our domain. And what I want to do here is I actually want to use a polynomial function that has a good representation of this. So that one has, let me see, yeah, I think this, give me 2 seconds here as I go over to my graph and try to pull one of these up and make sure actually the graph works. Alright, because my web browser vanished on me in the one. Alright, so let's see, what do I have here? X cubed. I am looking at, and I'm going to write this on the blackboard in a second. I just want to make sure that my my graph isn't showing over. Let me reset this here. Alright, so let's see, it's still not showing. Let's try that. There we go. Oh, that's not the right one. I'm not going to kick. There we go. That's much better. Alright, so this is a polynomial function. And let me turn this off here. And what happens with a polynomial function is I have a polynomial divided by another polynomial. But notice what's happening to it. It has some odd things going on with it. Zoom away from it a bit here. If I get really far away from it, it looks like a line running through. And that line is going to be important to us. We're going to develop what that line is. That's going to be called a slant asymptote. But as I get closer to it, something is happening up and down, and there seems to be a gap here, right? And this gap comes about because I can't divide by 0. And in this bottom function, there might be a place where 0 comes into play. And that's going to be called a vertical asymptote. And so what we're going to start defining is these things called asymptotic behavior. I'll actually show you a more clear-cut asymptote here. I'm just going to change this function over a little bit. I have x cubed minus 2x squared plus 1 divided by x squared. Again, I'm going to back away from this, and notice it looks like a line going left to right when I get really far away from it. That's the slant asymptote that it approaches. What's happening here is this line, or this part of the curve, approaches out here. But something happens down the middle of this. These two upward spikes around 0 are working their way off towards infinity. They're trying to get closer and closer to 0, but because if I look at my x squared here, I can't have x ever equal 0. I would be dividing by 0. And so we say there's an asymptote at x equals 0. And if I draw it in here, right, and so there is our asymptote at x equals 0. And it's a value that we can't have in our domain, but it influences the behavior of the function. These functions get close to that value of 0, which means they get close to that line, but they never touch it. And so an asymptote means that is a line that a function gets close to but never touches. And so rational functions get a set of asymptotes that are vertical. I want to come back to the blackboard here. So asymptotes are lines the function approaches but never touches. Gets closer and closer to these, right? And there are three types. There are vertical asymptotes, which happen where the denominator would equal 0. Right, and since we're calling the bottom function q of x, we would say these are the places where q of x would equal 0. So when we go to find our vertical asymptotes, they would happen where q of x equals 0 if they are not canceled out. And we'll see how that happens. They can be canceled out by something in the numerator. That doesn't mean you can have your function equal 0 at the bottom, but what it means is that there is no asymptotic behavior if it cancels out by something in the numerator. And we'll develop that idea. But in general, vertical asymptotes are, hey, my denominator, you're still looking at the graph. Did it do it again? Damn it. Thank you, Josh. There. This thing's been sticking a bit. I'm just writing down the definitions, so I'll go back to the words there. Thank you, Josh. I don't know why a couple of the windows, when I have gone back to them today, have switched over to other things. I'm going to clear out my cache and stuff. When I switched over to the graph and it showed you that curve wasn't even on my screen anymore. It was the screen I did earlier this morning. So I'm going to empty out my caches and stuff. Things are sticking on me a bit here. Alright, so asymptotes are lines that functions approach but never touch. And so the first type we have are vertical asymptotes, which is where the denominator would be 0. Now there is a way they can get canceled out and you can have non-asymptotic behavior, but you still have the denominator equaling 0. We cannot have an x value where the denominator equals 0. So we have to restrict our domain wherever q of x equals 0. And we had that earlier on with our functions. We said, hey, we cannot divide by 0. We had domain restrictions back in chapter 1 when we first started talking about functions. And they're here. They're here with everything we're doing. The other type of asymptotes we have are horizontal. And they happen when the numerator and denominator, I'm going to get my definition matching the books here, a horizontal asymptote, are when the numerator and denominator have the same leading power. Have the same leading power. Or the denominator has a greater power than the numerator. And we'll start building these. And then the third one is a slant asymptote. And it is a line defined by the remainder of the division. Because remember, a fraction is a division. And if these things have a remainder that make a line, these things are eventually going to approach that line. You can't see the blackboard again? Okay, it's back again. Whew, okay. Alright. So these are the definitions we're running towards. We're going to have asymptotes that are lines that these functions approach but can't touch. And the whole reason these things come into being is because of division and the possibility of dividing by 0. And so we're going to have to visualize these things in Desmos, and we're going to have to build them up. But our first step is always to look and to see what domain restrictions we have. So we're going to look for asymptotes in these functions. They're lines that will talk about what the function is doing as we get closer and closer to infinity. Asymptotic behavior takes over. Or as we get closer and closer to dividing by 0, asymptotic behavior takes over. As we go really far off, or we get really, really close to the domain restrictions. So our first job is domain restrictions. So let's look at a couple of functions, and we'll see if they are rational functions or not. And we'll also look to see what the domain restrictions might be. So the first thing that I need to have a rational function is I need a division. And so this passes the first test. I am dividing. The top needs to be a polynomial. So I can only have positive powers of x, no x in a fraction. And so let's see, is 2 of x minus 1 a polynomial? It is. And we'll make the denominator q of x. We'll keep this p and q nomenclature going through. The book uses it a lot. We used it early on when we proved irrational numbers. With the square root of 2, we used a p and q. P and q tends to get used for division a lot, so we'll keep it. This is also a polynomial. So this is a rational function. And so it will have asymptotic behavior. There will be things in this that we need to look for. Now, are there any domain restrictions? So we're given a polynomial, we're given a function. It has a division in it. We have to make sure that the numerator and the denominator are polynomials. And then we have to look at the denominator and say, hey, you can't equal 0. So x squared plus 1 cannot equal 0. So x squared can't equal negative 1. So x can't equal plus or minus I. That's okay, because our domain is coming from all real numbers. There are no domain restrictions for this one. Alright, this will always work for us, so we're good for any real number. And so this function here is a really nice rational function. It works for us, and it works across all real numbers. We don't have to leave anything out. So let's look at this one on the graph. Let me see if I can get over to Desmos smoothly here. Yes, good. And it's blank. Oh, that's exactly what I wanted. Alright, that sounds like whatever I kicked there, I kicked it properly. Alright, so our function was, so notice over here I'm typing f of x equals, and then I'm going to put in, what was it, 2x minus 1? Divide, I need to divide the whole thing, so I'll underline it all. And then underneath I had x squared plus 1. And here's my function. Now, it had no vertical asymptotes because there were no domain restrictions. I'm going to say this does have a horizontal asymptote. This does approach something horizontally as it goes off towards infinity. Right? If I go really off to infinity, there's a horizontal line there. And as I scroll in closer to it, we don't see it as well. But there is a horizontal asymptote. And it's at 0, but we'll get a rule for y. Right? But there's no vertical asymptotes because my domain is good for all real numbers. Sorry if I zoom in and out really quick. It's a really easy click, and I like the zoom function. I like looking at these things from very far away and seeing if they have a behavior that they all approach. All right, let's look at another function and how it relates to rational numbers. I'm going to have to export this out. Erasing my blackboard here. Zoom in. Zoom out. Alright, so the second function I'm going to look at, just to be different, I'm going to call it g of r, right? I use x a lot, and we really should recognize that our functions can have different variables. So just to look at this differently, I'm going to call it g of r, which is 1 over the square root of r. Alright, for this to meet our definition of rational function, that we need this to be a division with p of x over q of x. And so here my p of x is 1, and my q of x is the square root of r. So I have a division, but I cannot call this a rational function because the square root of r is not a polynomial. This is not a polynomial. Why does it keep doing this to me on the graph? Thanks, Eric. I will switch back to my monitor screen and see why this isn't switching over. I swear this had this on my feed before I flopped over. Definitely cleaning out all my cache and temp files once we're done tonight. My apologies, everyone. Alright, so I have g of r equals 1 over the square root of r over here. For it to be a rational function, my first test is there a division? Right? Do I have some function over another function? Well, I do. P of x would equal 1, and q of x would equal the square root of r. But the square root of r is not a polynomial. So we cannot say this is a rational function. Our definition of rational function is we need the division of two polynomial functions. And so this isn't going to have the behavior we're going to be talking about with rational functions. So there's a limit of what behavior we can get out of this. But I can still talk about, hey, that can't equal 0. Right? I can't divide by 0. And so I have a domain restriction Well, r also has to be greater than equal to 0 to be a square root. So we end up with r has to be greater than 0. And so the only domain we can get out of this is from 0 to infinity. So even though this is an irrational function, we can still talk about the domain restriction that it would have. And it gets both rules, right? The two functional restrictions that we have is our square roots cannot be negative. Right? We can talk about answers and roots with the square root being negative. We can talk about complex numbers as roots or answers, but we can't use them as the input for a function. And we can't divide by 0. So when I put these all together, the square root tells me that r has to be greater than equal to 0, but not dividing by 0 gets rid of the equal part of it here. And so all said and done, r has to be greater than 0. That's a lot of mental work for something that's not a rational function. And we will talk about these things a little bit later. I'm going to tempt fate and I'm going to go over to the graph. Wish us luck. Let's see what this thing looks like. Well, here is what 1 over square root of r looks like. All right, and we will develop things to talk about these functions in the next section of stuff. But for right now, this isn't meeting our definition of a rational function. And because of some limits on this, we'll just say, okay, it's not in the box we're looking at now. All right, let's try to go back to the blackboard. Switched on that one, switched on that one. Seeing if it switches for you guys. Hey, it did. All right, that's good. All right, I must have kicked it hard enough that time around. All right, let's look at one more function here. H of x, and I'm going to get x squared minus, x cubed, sorry, minus 2x squared plus 1 all over x squared minus 3x plus 2. So, I'm going to do the same test. I'm going to test if this is a rational function that we can work with, and then we're going to see if there's any domain restrictions, if it's a rational function, or even if it isn't. So our first, hey, we do have a division. So we can say p of x over q of x. All right? So it passes the first part of the test. There is division being involved. So we'll look at the numerator, p of x. Okay, that's a polynomial, so that's good. And q of x is a polynomial. So this is going to meet our criteria of a rational function. It is a division, and it has a polynomial in the numerator and denominator. So the next thing we have to worry about is q of x cannot equal 0. And so we have to find where q of x equals 0. We have to find the numbers that q of x cannot be. So we have x minus 3x plus 2 can equal 0. Well, we need to find the roots of this. And that's x minus 2, x minus 1 can't equal 0. So x can't equal 2, and x can't equal 1. right? So if I multiply these together, I get this. And we treat it like it's an equal sign, but we say, hey, you can't be those things. And so we can say, hey, x is an element of all real numbers, but x can equal 1 and x can equal 2. We can write it in set notation like that. Or we can say, hey, you're all real numbers, so you start at negative infinity. You get to 1. Then you go from 1 to 2. Then you go from 2 to infinity. Notice how writing this gets longer the more roots that we have in our denominator. I always said I like this notation. If you write down what x can't be, I've got what you're doing. Well, now we're online, so the book's going to ask it in specific ways. What is nice about this is this shows me on the graph, hey, I have a hole at 1 and I have a hole at 2. Possibly. Right. So let's look at what this thing looks like. All right, wish me luck. I'm switching to the graph again. Hey, we got that one there. Let's clean this out. F of x equals, and my numerator was x cubed minus 2x squared plus 1 all over x squared minus 3x plus 2. And I'm actually going to put in both of the asymptotes, because we said x couldn't equal 2 and x couldn't equal 1. And so notice here, on 2 there's a vertical asymptote, but on 1 there isn't. Right? But there is a hole in this graph. We can't exist. Right? We walk this graph and we come here, and we can't exist there. That point can't exist. But we have the asymptote here. And so part of our job is going to find out why there isn't a vertical asymptote at 1. Alright, I'm going to try to switch back to the blackboard. It shows that it's changed on my screen. I'm looking at your screen. Yes, alright. Sorry about the little extra delay there. Alright. Well, so what happens is vertical asymptotes are where the f value, whatever f of x is, shoots off towards infinity or negative infinity. Right? And so a rational function, whenever the denominator equals 0, it's undefined. But in some of those undefined places, in some of them, it'll cause a vertical asymptote. But in other places, it doesn't. And so we have to see what makes that function tick. Let's look at, let me get that graph back up here. X cubed, x plus 1. Alright, so let's look at that function we had previously. This is what we're going to end on, is the vertical asymptotes. We'll look at horizontals and the rules for horizontals to begin with. But I want to look at that h of x that we had, where we had, what was it, 3 x cubed minus 2x squared plus 1 all over x squared minus 3x plus 2. Now we factored what was downstairs. So we said x minus 2 times x minus 1. Well, let's look at this. Are there any roots or solutions to this? Well, it's a cubic, and it's a cubic that has possible plus or minus 1 as roots. Right? If I use the rational root test on it. So I'm going to put positive 1 cubed minus 2 times 1 squared plus 1, and that's 0. So this does have a factor of x minus 1 upstairs. Now, notice what I did here, okay? And I did it quickly. I did it off on the side. I used my leading coefficient of 1 and my constant of 1, and I did my rational root test. Because they were both 1s, I only had one possibility, or two possibilities, a positive 1 or a negative 1. So I put positive 1 in my function using the remainder theorem, and it told me, hey, this has a factor of x minus 1. Now I'll do my synthetic division here, so 1 minus 2, 1. Alright, so I take my leading coefficients from here. Oops, I have a 0 because I don't have an x term. So bring down my 1. 1 times 1 is 1. Negative 2 and 1 is negative 1. 1 times negative 1 is negative 1. Bring down negative 1. Right, so I'm really quickly running over what we've just been talking about in the first class. And I apologize for that, but that's why one of the things we built out of this. And so I use my leading coefficient and my constant to find my possible rational roots. I plug them into, I did p of 1 and I found that was equal to 0. So that let me know that was a factor. Right, I put my root of 1 in. Now I'm going to use quick synthetic division. Take the 1 and I take all my coefficients from here. Notice I have to have a 0 coefficient in here because I'm missing the x term. And that tells me that is how these functions factor. But notice those factors will cancel each other out. And so when I was seeing asymptotes on this function, and I'm going to go back to the graph now, I didn't see an asymptote when x equaled 1 because it was canceling out with a factor in the numerator. And so those two things were competing with each other and I couldn't zoom off towards infinity. Alright, I'm going to leave it here. We're going to talk, we talked about horizontal or vertical asymptotes. And I've shown the basics of vertical asymptotes. I want you guys to get your homework up to 4.5. It'll all be online. Get the homework up to 4.5. And start reading 4.6 and start thinking of asymptotic behavior. But what I wanted to do in this bridge over to this 4.6 and this rational functions was I wanted you to realize that the things we were doing in 4.1 and 4.5 are really important for making the stuff here work. And so I'm going to come right back in on next Thursday, starting right off with rational functions. We're going to do our horizontal asymptotes, but we're going to do these P's and Q's and these factorings a little bit quickly, right? But I wanted to show why this bridges over from the one thing to the other. All right. I want you guys to be safe. I want you to be safe and well, until we get to hang again. Remember, if you are trying to graduate or transfer at the end of this semester, let me know. We have a deadline of getting all grades in by the 13th of May. And so we want to make sure we keep those timelines. If you are coming back in the fall or in the summer and this is not graduation material, we can do an incomplete and have a little more time, and with all the things we're juggling here. So I need everyone to communicate with me what they're doing so we can help schedule these things out and make them work for everyone. Also, if you have any questions on problems doing the homework on Pearson, click the email my instructor, and I will try to put example videos up. I have not been getting as many example videos as the Chapter 3 stuff, which makes me guess you guys are just getting done with the Chapter 3 and you're just digging into the homework here and going through the videos. But if you need anything, send me the emails and I'll try to put examples up. Alright, I would strongly recommend using Desmos to graph functions that you haven't seen before, just to get an idea of its behavior. It is really, really helpful to look at these things. Alright, that's all I have. Keep being wonderful.